So we saw in our class yesterday, we developed some tools to parameterize a curve in either 2 dimensions or 3 dimensions. In principle, we could do it in any number of dimensions. And the morally speaking, what we were doing when we were parameterizing curves is something like the following. Right? So you give me some curve sitting in however many dimensional space that you like. Right? So here is my curve. Who knows what it does? And the idea behind parameterizing a curve is figuring out some way that we can identify a single variable that we call our parameter, t, and that single variable can distinguish all of the different points on this curve from one another. Right? The t equals 0 point is one of the points, t equals 1, t equals 2. So it's almost like what we're doing when we parameterize a curve is we're kind of setting up almost like a little number line along the curve. And the parameter sort of measures where we are along that number line. It kind of tells me how I could take the whole real number line and just sort of bend it around inside of 3 space to make this curve. So morally speaking, that's what it is to parameterize a curve. So as you might expect, to parameterize a surface, morally speaking, is to do the same kind of thing. So we have some kind of surface inside of 3-dimensional space. Who knows what it looks like? Maybe I'll sort of draw it like a Frito for a minute. So here is some surface living inside of 3D. And my goal when I'm parameterizing a surface is going to be to find a way of describing every point on this surface using parameters. The problem is a single parameter is probably not enough to describe every point on the surface, because if I'm standing on this surface, I have kind of 2 independent directions that I could walk, in contrast to a curve. So on a curve, if I'm moving around along a curve, let's say I'm standing here at the t equals 1 place, like what choices do I have on which direction along this curve to walk? If I want to move somewhere away from t equals 1, how many different directions can I go? Maybe a vague question, but this is actually important for both our discussion of parameterizations and also our discussion of limits a little later on today.
2.
Yeah, I kind of only have 2 choices. I can go forward or I can go backward, right? Forward here probably means the direction of increasing t, right? So I can go forward along the derivative of my parameterization, along r prime of t, right, the velocity vector, or I could go backward. And when we say backward, we really just mean in the opposite direction of the velocity vector. So those are really the only directions that I can walk along my curve, in the direction of the velocity vector or in the opposite direction of the velocity vector. That's pretty much it. And so since those 2 are not independent of one another, one of them is just -1 times the other, right? We can say kind of that there is 1 degree of freedom that we have. Like there's 1 dimension. A curve is a 1-dimensional object. If we want to be really specific about what dimension means, we have to be one of you who is taking linear algebra with me this summer. But that's sort of the main idea, is that there's 1 independent direction, forward and then backward, which is not independent of forward, right? It's just a multiple of forward. Whereas on a surface, if I'm standing at this point right there on the surface, how many independent directions do I have to choose from in which direction I walk?
Two?
Yeah, how can I think of what those 2 might be?
You can go left and right and up and down.
I could go left and right, I could go up and down. I could go north or south, or I could go east or west, right? So I might have 1 independent direction that kind of faces this way, right? You know, who knows which direction that it faces, but this gives me sort of 1 vector direction that we could go. I'm going to call this the, well, let me just call this direction 1. Or something like that. So I can go in that direction, or independently, I could choose to go in a different direction that is independent of the other one. And for our purposes here, independent is once again going to mean just not a multiple of, not parallel to. Linear algebra students, we will put that on a firmer foundation later in the semester, but I'll call this one direction 2. And since there's 2 independent directions that I can walk along a surface, we think of a surface as a 2-dimensional object. But it's the connection between these 2 pictures that I want to kind of stress for the moment. Because having one independent direction, like we do along a curve, we can sort of find one independent direction in this picture along my surface, right? Maybe direction number 1 is a direction along a curve drawn on my surface. So maybe I have some parameterized curve that lives on this surface, and I'll call that curve R1 of t or something like that. So here's a parameterized curve that lies on my surface, and if I'm standing at this point and I want to walk in the direction of direction 1 here, it means that I'm walking along a tangent vector to this parameterized curve. Right? So finding a parameterized curve within a parameterized surface is one really good way to help us understand what the shape of that surface looks like. It's just like when we were finding traces, vertical slices of graphs of functions a couple of days ago. Right? So I can have one parameterized curve that sort of describes for me, its tangent direction describes for me the first direction that I can walk at that point on the surface. And then the other direction could presumably be then telling me about another parameterized curve on my surface. And call this one R2 of t. Right? So the idea behind parameterizing a surface is that these 2 parameterized curves seem to be using different kinds of parameters, right? This curve's parameter sort of tells me how to go left to right along my surface. This curve's parameter is kind of telling me how to go up and down along my surface. So I should probably give those parameters different names. If I give those parameters different names, then I can kind of hold both of them in my brain at the same time. One of them is going to tell me how far up and down to go on my surface. The other one is going to tell me how far left and right to go on my surface. So it's a bit like having a map of the world or something like that and finding latitude and longitude. So tell me how to go, east to west, that would be a longitude question. Tell me how far north and south to go, that would be a latitude question. And as soon as you specify a latitude and a longitude, you have told me at what point on the map I'm located. Right? And so we need 2 parameters to parameterize a surface. So that's the big sort of obvious algebraic difference between a parameterized curve, where we only need a single parameter that we usually call t to parameterize a curve, and a surface where we need 2 parameters in order to do that. But the good thing is that we have a way to travel between these 2 worlds. Right? If I have a surface parameterized by a function like u of s and t, I can get a curve on that surface just by setting one of my parameters equal to a constant. Right? And if I do that, what I'm going to get is some curve that resides on my surface. And if I take the derivatives along those curves, I'm going to get velocity vectors that are tangent to my surface. So this is going to be another nice thing about surfaces, is that we can get direction 1, for example, here, as the derivative of this curve, right? But that this curve is probably just found by taking the derivative with respect to time of my parameterization, where I have kept t as a variable, but I have let s, the other parameter, be a constant. So I don't know, maybe this is 0, t or something like that, right? So when I set s equal to 0, that would describe this parameterized curve. And then when I take the velocity vector of that parameterized curve, I get a tangent vector to my surface facing in direction 1. Similarly, this second curve, the R2 of s curve, its direction 2 is just going to be the derivative of R2 with respect to the s variable here. And so it's going to be the derivative with respect to s of my parameterization, where s is a variable, but t is some constant. Maybe we'll make it a different constant. Maybe it's 3 or something like that. And that would be the case if this curve here is the curve where t is equal to 3. Right? So I guess the moral of the story here is, first of all, that we need two parameters to parameterize a surface. And second of all, we can get two tangent vectors to my surface just by taking an S derivative where t is held constant, and vice versa. The t derivative of my parameterization with s being held constant. And as long as my parameterization is nice enough that these two curves meet at a non-parallel angle, right? You could conceivably see where if two curves came together at the same direction, that those directions would not be independent. We would only get sort of one direction of tangency on my surface. But as long as they're independent of one another, those are going to give me two different directions that are both tangent and parallel to the surface at that point. And so what we would say is that those tangent vectors reside in what we would call a tangent plane to the surface at that point. So all of these tangent vectors here are going to reside inside of a plane that we would call the tangent plane to that surface. So unwittingly, this is giving us a preview into the differential calculus that we're going to be doing in this chapter that's coming up. Because just like in single variable calculus, where you have the graph of a single variable function, which is a curve, you find a slope of a tangent line to that curve using derivatives. Well, similar thing in multivariable calculus, where we have the graph of a two-variable function can be a surface, and the derivative, whatever that means, of that multivariable function is going to give me something like the slope of this tangent plane, except that planes don't have slopes. What planes have is normal vectors. And so ultimately what we're going to want to make the connection of is how can a derivative of a multivariable function give me a normal vector to the tangent plane of a surface? And the answer is a little bit different when we have a parameterized surface versus when we have a surface that's just described by the graph of some function of x and y. But those are going to be the different ways that we think about it, right? One way of getting a normal vector to a plane, if we know two parallel directions, we could take the cross product of those two, right? The cross product of this purple vector and this blue vector here would probably give me a normal vector to the tangent plane of this surface. So that would be one way to do it. So if we have a parameterized surface, that would be a way to get a normal vector to the tangent plane. But if we don't have a parameterized surface, we might want to do it some other way. So what we're going to do over the first half of our class today is come up with some strategies for how we might discover a parameterization for a surface. And we're going to do it in a few different ways. I actually do want to start with the first homework problem that's in the packet. Because parameterizing a surface, which is the graph of a function, is probably the simplest kind of parameterization that we can do. So that's going to be the question that we start with. I want to work through this one sort of together. And then when we go into the textbook problems, we shift gears just a little bit, because the surfaces that are being parameterized in the activities from the book today are generally not the graphs of functions of x and y. They're other kinds of surfaces that take a little bit more creativity to parameterize.